LOD2, Creating Knowledge Out of Interlinked Data. Welcome to the LOD2 webinar series, Linked Open Data Tools and Services for Publishers, Enterprises and Governmental Institutions. LOD2 is a large-scale integrating project co-funded by the European Commission within the FP7 Information and Communication Technologies Work Programme. This 4-year project comprises leading linked open data technology researchers, companies and service providers. Coming from across 12 countries, the partners are coordinated by the Agile Knowledge Engineering and Semantic Web Research Group at the University of Leipzig, Germany. LOD2 will integrate and syndicate linked data with existing large-scale applications. The project shows the benefits in the scenarios of media and publishing, corporate data intranets and e-government. Once per month, the LOD2 webinar series offer a free webinar about tools and services along the linked open data lifecycle. Stay with us and learn more about acquisition, editing, composing, connected applications, and finally, publishing linked open data.
University of Leipzig. Axel, the scene is yours.
Thank you. Hi everyone, my name is Axel Ngonga. I'm the main developer of the LIMES framework, and today that is exactly going to be my topic. So we're going to talk about LIMES within the linked open data to Lifecycle. I'll present the main ideas that led to the development of LIMES, some technical details as well. So basically state what the main components of LIMES are and how you can use them within your application. And then I'll show 3 demos. The first demo will be all centered around what I call the geeky approach to using LIMES, which is the very technical approach based on using XML files to configure and use LIMES. Then I'll show the native LIMES interface, which basically replicates the content of the XML files in the user interface. And then I'll show assisted linking, so basically how we can help you to create your link specifications. Alright, so before we start looking at LIMES, what is the linked data lifecycle that I talked about and that is at the core of the LOD2 project? Now we assume that to create linked data, you basically start with an authoring, so that is the orange circle in the picture. So you start by creating some form of data, usually in the RDF format. Once the data is created, the second step is then the interlinking and fusing of this data. So you basically want to take your data and link it with other knowledge bases and other knowledge sources that are available on the linked data cloud. Now, once you've carried out the linking, you want to be able to fuse, to consume the data, to enrich your own data with the data that's already available on the linked data cloud. That would be the third step, that is classification and enrichment. Now once that has been carried out, you want to make sure that the quality of your data goes beyond a certain threshold that you've set. So basically we also provide quality analysis methods for checking the quality of the data that you've integrated in your data. Now the segments that do not meet your quality requirements can be evolved and repaired. That is step number 5. So once you've done the evolution and you've repaired all the segments of your data is then ready to be used. And you can run plenty of different applications on linked data. We've mentioned a few such as search, browsing, exploration, and the like, but that could be basically any form of information that resides on top of your data. And that is basically where different users will then extract the parts of the data they're interested in, store them, query them, and indeed use that data to create even more data, which completes the cycle and takes us back to the authoring part or minor revision. Now LIMES is seated at the second step of the linked data lifecycle, which is interlinking and fusing. So LIMES is basically a link discovery framework. That can be clearly seen in this picture. This is the LOD2 architecture, and as you can see, we have LIMES seated in the interlinking API with other frameworks, and basically that is the API that you would call when you use the LOD2 stack to interlink your data with existing data sets. And it relies, obviously, or resides on top of other APIs that LOD2 provides. So that is basically gives you an overview of what LIMES is for and what its position is in the LOD2 stack. Now let's focus a bit more on LIMES. And the first question that one can ask oneself is, why was LIMES created at all? Now, if we look at the linked open data cloud, we notice two things. Number one, we have very large data sets. Data sets such as DBpedia have more than 1 billion triples. And these data sets are also very heterogeneous. They are on all kinds of domains, on all kinds of topics. On top of it, the data is very complex. Complex means in this particular case that the schemas according to which the data is described can be of very high complexity. If you look at the Yagonaga ontology, for example, there are thousands and thousands of classes in there. The same holds for the DBpedia ontology, where you also have thousands of classes and properties. And these are the kinds of knowledge bases that you want to be able to interlink your data to, or that might actually represent the kind of data that you have at hand and that you want to interlink with the linked data web. Now, given the size of the data sets and their complexity, we basically run into two main problems. The problem number one is a runtime problem. So if you imagine that you were just to try to link the cities in DBpedia with themselves, and each comparison, each similarity comparison took 1 millisecond, it would take you approximately a year to link the cities from DBpedia with the cities in DBpedia, so do a deduplication approach there. Now, given that, we basically wanted to create a framework that is fast, that is basically a framework that implements algorithms that allows to find links between entities across knowledge bases in a time-efficient manner. Now, to be able to support the complexity of the data sets, we also wanted to be able to provide means to create complex link specifications that then allow to specify very exactly how and when links should be created between different entities. And that is basically the purpose of LIMES. So we provide a framework that is time efficient in its computation, that can provide assistance during the specification of link specs basically. And on top of it, we provide different machine learning algorithms for allowing you to create link specifications. In this particular webinar, we are going to look at the first 2 points, so as at the time efficient computation and assistance during configuration. The machine learning will be the topic of another webinar. Okay, so what is LIMES? LIMES is a declarative link discovery framework. What I mean by declarative in this particular case is that LIMES assumes that it takes in a configuration and runs it. So basically there is a LIMES specification language with which you can specify how links are to be created, and LIMES can consume this specification and give out the links that you're interested in. As I said before, it is tuned towards efficiency, but also towards extensibility. The basic idea here is the following. We've implemented LIMES in such a way that all of the layers of LIMES architecture are what we call technically interfaces. So basically they can be extended at will by the user. It basically means that for your particular applications, you can extend each of LIMES layers at will and integrate the functionality that you need to be able to do the work that you need to get done. LIMES relies on a set theoretical grammar for specifying links. I'll explain that in a minute, and provides, as said before, time-efficient mappers for single data types such as numbers, dates, but also different types of strings and different measures. And on top of all that, machine learning for helping you while detecting link specifications. Now let's take a look at the LIMES architecture that I talked about before. We basically have 6 layers. The input layer, which is the bottom layer, provides means for reading in the data upon which the link specification, or the link discovery, is to be carried out. So we have modules that can read in character separated value files, modules for reading in RDF data serialized in different formats, but also modules for getting data from Sparkle endpoints. Now once you have your data, you want to pre-process it. So basically to put it into a format that will allow linking to be carried out in an efficient manner, and that will allow the link quality as well to be as high as possible. Now the pre-processing layer of LIMES allows you to basically do all that. It provides means for example, converting all your characters into a lowercase or uppercase. You provide string cleaning approaches for removing bits of strings that you don't need. But it also provides conversion algorithms that, for example, allow you to convert units from, say, Fahrenheit to Celsius. Now, once you've done all the pre-processing, all the pre-processed data is then stored in the data layer. And that is basically the layer upon which the mappers implemented in LIMES reside. Those mappers are the units of software that allow you to do the similarity computations as specified by a similarity metric. Now, once we've done all the similarity computations, we can then filter out the results and give them out. And there as well, LIMES provides different output formats that allow you to basically get the data in the format you want for further processing. The sixth layer, which is on the left-hand side, is the machine learning layer. Now, the goal of the machine learning layer is to allow you to detect specifications in an efficient manner. The idea here being that we have unsupervised and supervised machine learning algorithms that allow one to create link specifications when given knowledge bases as input. I'll show a bit of that when I present the third demo, but again, that's not going to be the focus of the talk today. All right, so how does LIMES look internally? How does LIMES work? It's actually pretty straightforward, but at the same time very different from the standard approaches. Now, LIMES assumes that it is given a link specification, a source knowledge base, and a target knowledge base. And what the controller does is first of all read the link specification and look especially at the similarity measure that is defined. Then it detects the different data types that are used in the similarity measure. And based on the data types, it then calls different mappers that are tuned towards processing those particular data types. Now, once the data is sent to the mappers compute then potential links in an efficient manner, and those links are then merged and filtered out, and that is basically what you get as output. So that's basically the core of LIMES. That's the LIMES workflow. Now, how does LIMES differ from other link discovery frameworks? Number one, it provides a very rich grammar that I will explain for specifying how links are to be generated. On top of it, it provides a hybrid approach. There are several ways of implementing a link discovery framework. Many approaches implement so-called multi-dimensional approaches, which basically means that they try to fit all the properties of resources within one multi-dimensional space and to do the linking within that space. LIMES follows a hybrid approach simply by splitting the task into different subtasks and running specialized mappers on each of the subtasks. And that's the third point, the third difference between LIMES and the other frameworks. It provides efficient mappers for each of the different data types and can then merge the result, and it's thus very time efficient. All right, so I've been speaking about link specification. What are those and how do they look like in LIMES? Now, a link specification in LIMES is composed of 7 main parts. The first part is the so-called metadata. That is nothing else than defining the prefixes that one needs for running the LIMES specification. This is what a typical set of prefixes would look like. You would have RDF, RDFS, or DBpedia, dropbank, and the like. And all you need to basically say is which is the namespace that is labeled by dropbank, for example, if you're using dropbank in your specification. Now, the second part of a LIMES link specification is the definition of the source and target. So you assume that you want to link 2 knowledge bases, those knowledge bases can be contained actually in a file or what format ever. Here we use the example of a Sparkle endpoint, the DBpedia Sparkle endpoint. So you need to specify the endpoint, the graph in case in your endpoint you have a particular graph that you're interested in. Also, you need to give the source or target a certain variable. That is the variable that you'll use when you then do the specification of the similarity measure. And you can also say how large a block should be retrieved from the endpoint at one go, as many endpoints do not allow to retrieve all instances at one go, but rather give out data in chunks. You can also specify a certain number of restrictions, which is basically those are properties that the entities that you're interested in linking must have. If you consider the example of linking drugs from DBpedia with drugs from drug bank, you wouldn't be interested in having animals or having cars or companies within the set of entities that you retrieve from DBpedia for doing the linking with drug bank. So you can specify that all instances you're interested in must abide by this particular restriction. And on top of it, one has to specify the properties of these entities that one would like to use for the purpose of linking. Now the core of a link specification is a similarity measure. If you have a good similarity measure, you can get links of high quality. So we spend a bit of time looking at the grammar that LIMES provides for specifying similarities. Now, as I said before, LIMES provides pre-processing functions that allow you to transform the content of property values. We have pre-processing functions for strings, numerical values, but also data converters. On top of it, we provide different similarity measures for strings and numerical values, and those can be combined. So basically, a similarity measure always expects either a pre-processing function, so the output of a pre-processing function, or the output of a property. So this is an example of what such a segment of a similarity measure could look like. You could say you want to take the label from the first knowledge base, from the source knowledge base, convert it to lowercase, and compare it then via the trigram measure or trigram measure, depending on where you come from, compare with the labels of the entities in your target knowledge base. Now, on top of it, we provide different types of operators. The idea behind an operator is to provide means to combine different similarity measures to improve the quality of the linking. Now, we have two main types of operators in LIMES. The first are so-called measure operators. So the measure operators do nothing else than combining the results of measures and generating a new measure. So for example, if you were to combine, if you had your first measure being the similarity of the labels of the entities in the source and target knowledge base, and the second similarity measure being the similarity between the label in the first knowledge base and the name in the second knowledge base, you could combine these measures by using, for example, the maximum operator. We obviously do provide other operators for merging measures. We also provide so-called specification operators. Now, specification operators, instead of operating on measures, operate on whole specifications. So you can basically combine the results of several specifications. The difference between the measure and specification operators is also that specification operators allow you to specify filters for filtering out the results of different specifications and then merging them. So for example, if you had the first specification that was trigrams on labels from the source and label from the target, and the second specification that was trigrams from label and names, you could then apply a filtering operator to the results of these specifications and then merge the results via operators such as OR and div and the like, so set theoretical operators. All right. Now, the other parts of a link specification with respect to LIMES are the acceptance conditions. So basically, that's where you say you set the thresholds for saying when the similarity measures or the similarity of two entities is beyond this threshold, then we'll assume that they are to be linked by the relation that are specified. For example, here we said if the threshold is beyond, or if the value of the similarity is beyond 0.9, then we can assume that the entities are to be linked via our same as. We can do the same for review conditions. So LIMES will write two different files, an acceptance file and a review file. In the review, usually the review threshold is lower than the acceptance threshold, and that is where you would store the entities where you want to do a manual review. And you can also set an execution mode which tells LIMES how to run the similarity computation and set an output format as shown before. I hope that that was clear. So now I'm going to present LIMES within different demos, so to give you a taste or an idea of what it looks like when one really uses LIMES. I'll start with the geeky approach. The idea here is we want to specify how to extract our same as links between two knowledge bases. The source knowledge base here will be DailyMade, which contains a lot of information about medication, whilst the target knowledge base will be DrugBank, which basically also contains data about different drugs. So we want to be able to create links between those. And the features that I'm going to show is how to define a source, how to define a target, how to define similarity measures, but also how to use property chains for linking. So what we exactly want to do is find active ingredients from the one drug and link them to the other drug, the drug in DrugBank. So in this particular case, it is not looking for our same as links, which is the most common use of link discovery frameworks. We can actually do way more with them. So as I said, I'll show you how to use source target measure. I'll show you how to use property chains for linking, but also how to define pre-processing within a LIMES link specification. All right. Now, this is the link specification for that purpose. As you see, we start by defining a large number of prefixes. So basically all the prefixes that we need to be able to specify the similarity measures or the restrictions need to be predefined here. An example of how that would look like is we say for this particular namespace, that is the DailyMade namespace, we'll use this particular label. And the same holds for DrugBank. Now, the source definition, basically I use a local endpoint to make sure that the demo works and that there are no internet problems here. You can define an endpoint. This is the graph that we're going to use. We set the variable for this endpoint to X, and the page size to 1000, which basically means that we'll always retrieve 1000 triples at a go. The restriction is we just want to look at DailyMade drugs, so we're only interested in linking drugs from DailyMade to drugs from DrugBank. If you look at this particular property definition, you will see two interesting things. Number one, the property value that we use is not the property value that is directly attached to the drug X. Actually, it is the RDFS label of the active ingredient within X. So by this means, we can use property chains. So by using this particular operator between properties, we can define chains of properties whose values are to be attached to the entities that we're interested in linking. In addition, we use a pre-processing function here, and we say as lowercase, which basically means that the pre-processing function lowercase is to be attached or to be carried out on this particular property value before the linking happens. Note that we can define sequences of pre-processing here. So we can define pre-processing chains simply by using the minus and then superior operator. So basically, by using an arrow, we can say use the lowercase and then use this and then use that before then you do the linking. The definition of the target is obviously very similar because that's just the target knowledge base. So it's just another knowledge base, and as you can see here, we also use some pre-processing. The similarity measure is then given by this means. We say we want to use the trigram similarity on the RDFS label of the active ingredient and the RDFS label. We set our threshold here to 0.9, and this is the output file. So we chose, in this particular example, to give out the data as turtle. Now, all you need to run LIMES, let me just clean my screen real quick. All you need to run LIMES is basically Java 1.6, and obviously the LIMES library. And the command that you then have to give in is obviously Java -jar because you're running a jar file. Then you have to call the jar library, the LIMES library, I'm sorry, and then give where your link specification is to be found. So basically this is the path to our link specification. And once you press enter, what LIMES does is read the data from the source, read the data from the target, and carry out the mapping. It's already done, as you can see. We've carried out, so the complexity of the problem was, as can be seen here, 2,722 times 4,772. So those are the numbers of entities that we're supposed to carry to compare. And if we had carried out all the comparisons that lasted quite a long while, the LIMES is able, through the algorithms implemented in it, to basically reduce the complexity of a program so that we can compute all these links and write out all the data in 1.662 seconds. Okay, so much for the geeky approach. Now let's look at a different problem for the second step. So how do we use LIMES native interface if we don't want to have to deal with XML, for example? Now, I'm going to show you that in the second use case. The idea here is we want to link drugs from Wikipedia with drugs from DocBank by using our same as links. So this is the LIMES native interface that can be found at limes.aks.q.org. And here you can basically specify, simply fill in the form for a link specification, press the run button, and get the links that you're interested in. So it's basically the same as the content of the XML file as showed before. So all you do is specify the source and the target over here. And the most important field, the metric field, where you basically type in the kind of similarity measure that you want to use. Note here that we use the filtering operator. So our first similarity measure is the trigram of the labels and the generic name, and we filter that by using a linear filter that basically sets the threshold to 0.8. So basically the first specification would be this section, and we filter the results out by getting rid of everything that's below 0.8. Then we do the same thing for the second specification, and then combine everything by using the OR operator. Now, we also set different thresholds for acceptance and review, and obviously the relation with which we want to link all these things. Note that when you specify links here, so basically when you specify property values and restrictions, we also have an automatic prefix detection that fills in these forms for you. But in case you happen to find a form where it's not filled out, it simply means that we weren't able to find it. You will need to fill it out manually before running the link specification. Now, we can press on start linking, and what basically happens is that the data is read from the cache and the linking is carried out. As you can see here, what you get is a large number of statements. Those are basically the drugs that have been found to be equivalent. And in the review data here, you basically have one drug that didn't make the cut. So basically the similarity is between 0.8 and 0.9, and this is what would have to be checked manually. All right, so this is the native interface. The third thing I want to show you is basically the Colanote interface. So Colanote stands for complex linking in a nutshell. And the idea here was to provide assistance to the user while he's doing the linking. So what we basically do is provide suggestions for the different classes that should be linked across two knowledge bases, but also for the types of properties, so basically for the mapping properties that should be used within the linking process. Let me show you how that works. So here we have two endpoints. The diseasome endpoint contains descriptions of diseases. The CIDR endpoint, which is the side effect knowledge base, considers diseases to be side effects. So basically, all the user has to do here is specify the endpoints that he wants to use and basically the graphs that are to be used and press on OK. The algorithm in the background then tries to figure out which classes from the first and the second knowledge bases actually match. And you can see here it figures out that diseasome disease should be the same thing as CIDR side effect, which is something that you wouldn't find out if you simply use something like string similarity on the class labels. Now when you press the Find Property button, the matching properties are then found, and the algorithm then presents this interface that allows you to specify, to generate link specification in a graphical user interface. Now the interface has quite a few features. If you look over here, you'll see that these different property names are color-coded. But if you then click on the target property, you see exactly the same colors. So basically, by these means, ColorNote suggests that if you want to use side effect, for example, you might want to connect it with RDFS label on the other side of the, basically the other knowledge base. So basically, the target property side effect can be connected with the source property RDFS label. In addition, ColorNote already provides a first link specification. The properties that are used here are the properties that have been found to match best. So basically, just by pressing the button OK, OK, you already get a first link specification. If you then want to improve it, you can basically provide all the functions that the LIMES kernel provides in here. So let's see what we can do here. Let's say we're not happy with the RDFS label matching via trigrams. We can say we want to compare, in addition, the diseasome name, so from the first knowledge base, with, say, the side effect name from the second knowledge base. I also want to have some form of pre-processing, say lowercase. So basically, we want to transform everything to the lowercase. We can simply click from the source, so from the blue square to the yellow square to connect that. And we say we want to do the same thing on the other property value. All right. Now we can choose a measure. So we have different string measures and number measures. Because we know that these are actually strings, let's say we take the trigrams again. So we can combine those. As you can see, we still need to connect that to the output. So we need an operator that will combine this section of the specification with this other section of the specification. There we can either use a measure operator like min, max, average, or linear combinations, or basically a set operator, which is a specification operator. Let's say we use the maximum. We then need to disconnect this and put it in here, and do the same over here. Connect that to the output. And we're done. So basically we've created a new link specification fully graphically, and the tool already suggested a link specification that would actually have worked. So all we need to do now is generate a config, and the tool allows us to download the link specification, which would look exactly like the link specifications you've seen before, or execute it on the LIMES server. So that's basically the third way of using LIMES. Right. Before we conclude, a couple of technical details with respect to LIMES. As I said before, LIMES was implemented fully in Java, so the main requirement for using LIMES is Java 1.6, and it is run under the Creative Commons license 3.0. You can get all the information you need under this link. And I also wanted to point out a couple of technical papers for the people that are more interested to detail things, so into the detailed workings of LIMES. The first paper is a paper that was published at the ontology matching workshop last year that basically presents the core of LIMES and how the core of LIMES works. But we've also published some papers on the machine learning algorithms implemented in LIMES that I'll present in another webinar. But if you're interested in that already, you can look at the Raven paper that was also presented at the workshop on ontology matching, or you can come to ESWC and see the newest work that we've done that combines active learning and genetic programming. All right, that was it from my side. Thank you very much for listening, and I'm be happy to take questions now.
Thanks, Axel. There are indeed some questions, but first of all, the question that comes nearly every time, if this webinar is recorded, and yes it is, you can watch it after some time when we converted it. And the first webinar related question is if you please can go deeper a bit and show us or discuss with us about the differences between LIMES and Silk. Is there any similarities? Is there any advantages of LIMES?
Sure. In the paper that I pointed out, we did do some comparisons of LIMES and Silk, especially with respect to runtime. And the main difference between LIMES and Silk are the approaches that are followed. So basically, Silk has a multi-dimensional approach. The idea there is that you take all the property values that you want to compare and you put them in one space and do all the comparisons there. LIMES follows their different approach. We try to have, as I said, as you can see on this particular slide, we have specialized mappers for the different data types. The main advantage is simply that by this means we can run way, way faster and we are more time efficient. And I would definitely suggest that you look at the ontology matching paper where we've done some evaluation in that respect. And we've also got another paper coming up soon where more comparisons have been done. I hope that answers the question.
I think so, yes. If no, please, dear listeners and watchers, grab it up again. Another question was if there is new data sets created while linking the sources.
No. The basic idea is we create new data that you can integrate in your source. So when you do linking, you have a source database, or a source knowledge base, I'm sorry, and a target knowledge base. And what you want to create are links, right, between the source and the target knowledge base. And those links, that's basically new information that you can integrate in the source or in the target knowledge base to make it basically more linked, which is at the end the aim of the linked data cloud.
All right, thank you.
Any further questions?
Yeah, there are two left at the moment. The question was if LIMES is open source and if I could run it on my, or if I could run my own LIMES.
It is definitely free to use by any person in the academic domain. So basically, the next release will come out soon. We hope to have it done before the end of May. And sure, then there will be a downloadable jar file that you can simply take and run locally, definitely.
All right, thank you. By the way, for anybody who's interested in the technology stack of LOD2 in general, there is a possibility to download and to play around with the versions that are available at the moment at lod2.eu. But there is another question. Could you please grab up the point how LIMES is doing matching of classes?
Oh, sure, definitely. We used so-called stable marriages algorithms. The basic idea is that we look at the source knowledge base and the target knowledge base, and we basically try to figure out how similar they are by looking at the property values that are assigned to them. The problem there is that you basically generate a huge graph, and you want to know out of this huge graph which classes match which other classes best. And that's where stable marriage algorithms comes into play. The basic idea there is that it's like a certain number of people meeting a certain number of people and trying to be coupled together. You basically allow the first group to propose to the second group, and the second group can accept or decline. And if you run that algorithm in a linear number of times, you basically at the end have the best possible matchings between the classes. And that's basically what we do here as well. So basically we have a similarity function. We run it across the different classes. We run to be technically more precise, the hospital residence algorithm, which is the same as stable marriage. And we get the best matching classes, and those are the classes that we suggest to the user. And if you want more details on that, we've actually published that in the paper that I'll show you in a minute. That was, I think, the last paper in my list, yes. So the Raven algorithm, it is explicated there how we do that.
All right, great. So far, that was the last question that we collected. And then it basically comes to the point to lead to the outro as a preview as well. Hope you had a good time and enjoyed staying with us. If you need more detailed information, please visit us again at www.lod2.eu, and please let us know how we can improve to meet your expectations. Axel, thank you very much for giving us an insight.
My pleasure.
Hope it was good for you too. And last but not least, please do not forget to register for our next webinar, and have a great day. Goodbye.
Goodbye.
Hope you enjoyed staying with us. If you need more detailed information, visit us at www.lod2.eu and let us know how we can improve to meet your expectations. Don't forget to register for our next webinar. Have a great day and don't forget.
It's the end of the web as we